So far in the course, we've looked at three related concepts: limits, continuity, and differentiability. Let's explore how that all plays out, or how those all connect in the function absolute value of x. If we draw the graph of that function, labeling it x and y, on that scale, our function looks like the traditional absolute value. And we could put some numbers on here, call that 4, 4. So each grid point is one value. And we get these pure straight lines throughout this graph. Now at any point on the right here, all the way along here, the function is clearly differentiable. And we can also say it's continuous. And if it's continuous, the limits are defined, or the limits exist. If we pick any point and say, what happens to the function as we get closer to it, there is an answer to that question. The same is true all the way along on the left-hand side. Pick any point you like. We can define a tangent line, and we can talk about the continuity. We can draw it with one pen stroke through that point, through to the neighbors, and we can talk about the limit existing. Where do things get interesting? Well, down here at the bottom. This is our problem point. So let's dive into that. First off, let's talk about limits. The limit as x approaches 0 of the absolute value of x is asking the question graphically, what happens if we come down from each direction? Do we end up at the same place? And absolutely. Whether we come from negative values of x and head them towards 0, we're going to end up at 0 in the end. And if we come from positive values of x and head down, the absolute value numbers are also going to head towards 0. So the limit is a nice finite value. It exists and has a value 0. Furthermore, the absolute value of x is continuous at x equals 0. We can see that graphically. We can draw it with one straight or one continuous pen stroke moving from the left to the right. Where do things break down? Well, it is not differentiable at that point, at x equals 0. Absolute value of x is not differentiable. We can see that we have a cusp, or from a more intuitive or graphical perspective, the slope we would get coming in from the left is negative. If we ask what's the slope at this point coming in from the right, it would be positive. And so we have a disagreement about what the slope has to be. And if there's not a single answer for a derivative or the single answer for a slope, we say there is no single slope. The derivative does not exist there. Now, can we be a little more assertive about that, a little more rigorous about that idea? And absolutely. We have the derivative as a definition. It is the change in f over the change in x. It's a slope. But it is a slope that we get as we let x, or delta x in particular, approach 0. Now for our absolute value function, where that gets interesting is when we come from the left and we pick 0 as one point and we pick some other point on the axis, delta x here, we're going to get different slopes than if we pick 0 and a delta x that's positive and ask what the slopes are between those 2 points. So what we're going to have to do here is take the one-sided limits, because there's a difference between what happens in different directions. That's better. So let's take, first off, the x going towards 0, delta x going towards 0 from the positive values. So what that means is we're talking about a delta x in this range here. And then what are we comparing? Well, we want to do this at the point x equals 0. So we're going to use x equals 0. Our change in f, how does our function change? Well, it's the absolute value of delta x plus 0 minus the value at 0 all over delta x. This is our function value at x plus delta x. And this is our function value at x, using the original definition ideas, and then we divide by the run on the horizontal axis. So it's rise over run in much more complicated math-looking terms, but the idea is exactly the same. It's the slope of a line. The nice thing we can do here is let our delta x get smaller, but all of this simplifies. Delta x plus 0 is just delta x. And on the bottom we have delta x as well. Well, that's straightforward to deal with because this, when we approach from the right, guarantees that delta x is larger than 0. So larger than 0. And that means the absolute value of a positive number is just the same number again. So we use that idea, and we can write our updated equation here. X approaches 0 from the right, and this time we can simplify the absolute values as just as delta x. And of course, that's just going to equal 1. Those cancel perfectly. What does that mean again? Going back to the picture, when we pick a step in x that is positive, when our delta x is positive, take any 2 points, connect them and find the slope, you're going to find a slope of positive 1. Now what happens if we come from the other side? You should be able to make a quick prediction right now about what we'll see when x is coming from the left or delta x is negative. Think about it for a moment. And then we'll dive into the definition. Same idea. In fact, everything is exactly the same here so far. The only thing we're changing is how our delta x relates to 0. That means this first simplification ends up the same way as well. Delta x plus 0 is just delta x, still in the absolute value, and delta x on the bottom. What changes now is that delta x is going to be less than 0. And if we're working with absolute values, we have this counterintuitive result that if I have a negative number and I take its absolute value, think of minus 2. Let's do that in parallel here. I would get plus 2. But one way to get there is to take the value we had and make it negative. So this is what we started with, and we get the positive version by multiplying by another negative. We need to be able to do that here because we don't actually have numbers where we can see the signs. The best we can do is replace the absolute value delta x. Because what's inside is negative, we want to make it positive. We're going to have to multiply by yet another negative. That makes this whole thing positive overall. And we see that we get the same kinds of cancellation except with that negative sign. So if you guessed earlier that the slope coming from the left was negative 1, you're absolutely right. And we see that these two values are different. These differ from each other. And what that means is, going back to our limit ideas, if we have a limit from the left and a limit from the right that differ in value, then the limit overall of our slope does not exist. And because this is the very special limit of slopes delta f over delta x, if it doesn't exist, then it means there's no unique slope at x equals 0, and that means the function is not differentiable. Use a little shorthand here, at x equals 0. So all of this work validates our simple idea from the last page, where we looked at the graph and said, oh, there's a cusp here. Why is that a bad thing? When we go back to the definition and using formulas, we see that we get different slopes coming from different directions, and if that happens, we can't talk about the thing that makes the derivative, the thing that defines the derivative, existing in that case at x equals 0, and so we have the conclusion the function is not differentiable at x equals 0. In that last example, we compared these three ideas, or we used these three ideas. The limit of the function existing, the function being continuous, and it being differentiable. These are not three random properties or three independent properties. If you get one of them, then you have some conclusions about the others. In particular, if you have a function that's differentiable, then you are guaranteed that it's going to be continuous. Anytime you draw a differentiable function, then you're going to have a tangent line, and to have that tangent line, you have to be able to draw the graph in one stroke. It doesn't necessarily work the other way, though, because we might have a function that's continuous, like absolute value, but that has a cusp, so it may not be differentiable even if a function can be drawn in one pen stroke. The same thing applies to the limit existing at a point. If we have a function that goes and behaves like this and has a hole and then keeps going, the limit exists, but it's definitely not continuous. And because there's nothing in terms of value defined there, we also can't define a slope, so it's also not differentiable. So the hierarchy is, if a function is differentiable, then it is continuous and the limit exists at the point we're talking about. It's not always guaranteed to go the other way, though. It's possible to have the limit exist and not be continuous, or it's possible to be continuous at a point but not be differentiable. Now, an important note after focusing on all these odd cases, at the end of the day, it is really, really common to have functions that are differentiable everywhere or almost everywhere. This function has slopes anywhere you care to pick. There's no problem there. You can define a slope of a tangent line. The only time you get problematic slopes is maybe with things like the tangent graph. Well, there the function isn't even continuous at various points and has all these asymptotes. So there might be some points, but everywhere else, every other point you pick on the tan graph, you're going to have well-defined, unique slopes of tangent lines. So by and large, most of the time things are continuous. Most of the time, those same functions are not only continuous, but differentiable. So just keep in mind, this is something to be aware of, but it's not a very common problem in most day-to-day things. It's just one of those gotchas that can appear when functions misbehave a little bit, either because they're piecewise or they have some asymptote kind of behaviors, things that would usually raise some red flags before you got too far into the analysis anyway. Where that leaves us then is investigating what these multiple slope values of a graph will actually mean, and that's how we're going to spend most of our time going forward.